So today we're going to be graphing exponential functions, and we're going to be able to graph them and use the models when appropriate. So the first thing we're going to look at is just a definition. So the exponential function f with base a is denoted by f of x equals a to the x for every x in the real numbers where a is greater than 0 and a is not equal to 1. So basically, remember f of x is the same thing as y, so we're going to just be dealing with y equals a to the x. Now it says a has to be greater than 0, so this value is always going to be positive. And then it says that, so I'll put positive here, a cannot equal 1. So this little bubble on the side is asking why is a equal 1 excluded? So why can't we have a equal to 1? Well, let's think about it. If we have a as 1, no matter what we plug in for x, like if I plug in 2, I'm going to end up with 1 because 1 squared is 1. If I plug in 5, 1 to the 5th is 1. If I plug in 100, I'm going to get 1. So no matter what I plug in for x, my y value is always going to equal 1. So we'll say 1 to any power will always be 1. And then if you were to graph what every x value has a corresponding y value that's 1, it would end up being a graph that is a horizontal line at y equals 1. So it would always be the horizontal line y equals 1. So when you have an exponential function, a is never going to be equal to 1. So let's kind of look at the general graphs for these functions. So if you have y equals a to the x, and a is greater than 0 and a is not equal to 1, the general shape of this graph looks like this. Okay, and this is called an exponential growth, okay, because it's growing. From the left to the right, it's going up, so it's increasing and it's growing. Now, we have a couple features of the graphs. So in this particular graph, we have the domain is all real numbers. So for all of these functions, these exponential functions, you're going to have all real numbers for your domain. The range is going to be y is greater than 0. So it's not greater than or equal to, it's just going to be greater than, because y can never be 0. If you plug x values in to this equation, you're never going to be able to solve and get 0. And also, you're never going to be able to get any negatives, because if a is always greater than 0, and a is always positive, no matter what we plug in for x, it's always going to be a positive value. Even if we plug in negative values for x, remember a negative exponent brings the number to the bottom, so it just becomes a fraction. It's not becoming negative. So your range is always going to be y is greater than 0. In this case, the y-intercept is going to be 0, 1. Okay? Because we know that when we have a y-intercept, the x value is always going to be 0. So if I plug 0 into here, anything to the 0 power is going to equal 1. So the y-intercept will be 1. And then we have this thing called the horizontal asymptote. And the horizontal asymptote is going to be y equals 0. That's like our little boundary line where the graph can't go below. So it can come very, very close to 0, where y equals 0, but it's never going to actually touch it or cross it. Then we have end behavior. So just like when we did end behavior with polynomials, we have end behavior for exponentials. So again, we have a left end and we have a right end. So on the left end, as x is getting more and more negative, so as x approaches negative infinity as it goes towards the left, the y is going to approach 0. So it's not going to negative infinity since the graph is not going down below the x-axis. So it's getting closer and closer to 0. On the right side, x is approaching positive infinity, it's getting more and more positive as y approaches positive infinity. When we have an exponential decay function, that's when we have y equals a to the negative x. So this graph is going to look similar to the other graph, but it's going to be decaying or declining. So it's going from left to right, it's getting smaller, your y values. So again, the domain will be all real numbers. These functions always have all real numbers. The range, again, for a decay function is going to be y is greater than 0, since you still can't have negative y values. And then the y-intercept will again be 0, 1, since if you plug 0 in for x, you're going to end up with 1. And the horizontal asymptote, again, is going to be y equals 0. So they're very similar. The only difference here is that decay is going down, the growth is going up. So when we look at the end behavior for these, on the left end, as x approaches negative infinity, y is approaching positive infinity. On the right end, as x approaches positive infinity, y approaches 0. So they're kind of flipped from each other. So here's the concept summary. So you have a function, y equals a b to the x. A is greater than 0 and b is greater than 1. Then that means it's an exponential growth. So you have two variables here. Now b is like the a that we saw in this example. Okay, so whatever's attached to that exponent, so in this case the b is attached to the exponent. So b, if it's greater than 1, it's a growth. If b is a fraction, if it's between 0 and 1, it's a decay. A always has to be greater than 0. Okay, in either case, the y-intercept is 0, a. The domain is all real numbers. The asymptote is y equals 0, and the range is y is greater than 0. So everything is similar. We're just going to look at the a and b values that were given. So we want to identify each function or situation as an example of exponential growth or decay, and then find what the y-intercept is. So if we look at a, we have 3 as our a value and 4 as our b value. So since b is greater than 1, so since 4 is greater than 1, this is an exponential growth. And then the y-intercept is going to be 0, a. So 0, the a value here is 3. So whatever number is right in front will be your y-intercept. So in the previous examples, we said the y-intercept was 0, 1 because there was nothing else in front of the a. So this was like 1a to the x, and this is 1a to the negative x. But in this case, we have a 3 in front, so that becomes our y-intercept, since if we plug a 0 in for x, 4 to the 0 would be 1, and then 1 times 3 is 3. Okay, in b, we have 0.75 as our x value. That is between 0 and 1. This represents an exponential decay. And again, if I plug in 0 for x, 0.75 to the 0 is 1. So 0, 11 is going to be y-intercept. And now C, looking at an application, so you put $2,000 into a college savings account for 4 years. The account pays 6% interest annually. So just think about this. If you have an account and it's paying you interest, are you gaining money or are you losing money? Is it growing or is it decaying? So since you're going to be gaining money, this is a growth. And then our y-intercept here, if x is 0, so time is 0, when you open this account, how much money do you have in the account? So when it's 0, you have $2,000 in the account because that's what you're starting with. Now if we look at some of these graphs, when you're graphing an exponential, you want to make a table of values. Now unlike the radicals, you don't necessarily have to pick any values that make sense. You're just picking whatever x's you want to pick. The only thing that you have to make sure that you do is pick some negative x's and some positive x's. And you always want to include 0 so you have your y-intercept. So I'm going to make an XY chart, and I'm going to plug in -2, -1, 0, 1, 2. And those are just easy to plug in, and they're near each other. So literally you can plug this right into a calculator. So you can do 2.1 to the -2 power and then times 4. So you're going to get decimals for these, which is fine. Okay, so when I plug in -1, I get 1.90. When I plug in 0, I get 4. When I plug in 1, I get 8.4. And when I plug in 2, I get 17.64. So then we just So again, these shapes are going to be similar for all these exponentials. They're going to look similar. And then we need to find our y-intercept. So the y-intercept is where x is 0. So in this case, the y-intercept is 0. Okay, so let's look at one more. So again, we're going to make a table of values. So I'm going to make x, y. And I'm going to pick, again, -2, -1, 0, 1, 2. So if you're one of those people that likes to have a set way of doing something, if you pick -2, -1, 0, 1, 2, you're good. So you just want to make sure you have some negatives, you want to have 0, and you want to have some positives. And the smaller the value of x is, the easier it is to simplify. Now when we plug this in, because the exponent's a negative, 3 to the -x, when I plug in -2 for x, that becomes a -2, which becomes a +2. So when I plug in -2, I get +9. 3 to the -1 would be 3 to the first, which is 3. 3 to the -0, that's just going to be 1. 3 to the -1 is going to be 1/3. And 3 to the -2 is going to be 1/9. So now I graph these. 9, higher values of x. Looks something like this. And then you need your y-intercept. So here our y-intercept is going to be 0, 1.